Okay, so this is lecture 4, Foundations of Pure Mathematics, and we're going to have some indirect proofs today. So let's see how these work. First, we're going to need a bit of notation and definition again. So we're going to look at non-empty finite sets which have just got real numbers in. So these are pretty easy sets to work with, like 1e pi root 2, which are not in the correct order at the moment. Okay, that's a set with 4 different real numbers in. You can check. And but more generally, if you've got n elements, where n is some positive integer, it's going to look like this. The empty set does count as a finite set. The empty set's a peculiar special case. It's the only set with no elements in. Naught is not a natural number, though. So that's why I made sure I said non-empty set, because the empty set gives trouble. There's a non-empty finite set of real numbers, and you can write them in strictly increasing order. That you can prove by induction, actually. But if you really wanted to do it, I'll take that as self-evident. You can go away and think about how you would prove it, that every finite set of real numbers can be written in strictly increasing order. I'm going to assume you can do that, and we'll start from there. So generally, if you write down your finite set like this, they might be in the wrong order. So then you might have to reshuffle them before you finally get them into this form, so that S1 is actually strictly less than S2, strictly less than, and so on, up to strictly less than Sn. Of course, there's only one element, then you don't have any choice, and it works straight away anyway. Okay. Once you've got them in that order, then, because there's only finite elements in the set, there's none of these issues with that you're going to meet in ACF involving infinite sets, which may or may not have maximum or minimum elements, but then sometimes they're bounded above, and then you've got what's called the least upper bound, or the supremum you'll come across, and there's a supremum and an infimum. We don't have to worry about any of that as long as the set's only got finitely many things in. So that's what we've got here. And I've written them in order, and I just want to pick out S1 and Sn to be the minimum element and the maximum element, and got the notation min S, the minimum element in S, max S, the maximum element in S. And this doesn't work if you've got sets with infinitely many elements in, even if they're bounded sets. You can have a bounded interval which doesn't have a maximum element and doesn't have a minimum element. Like an open interval has no maximum element, it's got no minimum element, even though it's a bounded. The open interval between of all real numbers strictly between 2 and 4 doesn't have a maximum element, it doesn't have a minimum element. So you have to watch out for that. And you'll see lots of that in ACF. Right. So now I want to talk about common factors, which you could also call common divisors. And the highest common factor is also known as the greatest common divisor. I've been using the word factor for the last couple of years, and so I'll carry on with that. But I know a lot of people who prefer the word divisor, and because I'm talking about positive integers to be either factors or divisors in this module, it doesn't matter whether you use the word divisor or factor, I don't care. Right. Now, if you take a non-zero integer, then there are only finitely many different positive factors. That's because any factor of n has to be between, you look at the numbers 1, 2, 3, up to n, and some of them will divide into n and some of them won't. Okay? But nothing strictly bigger than n can divide into n when n's a positive integer. So why did I have to say that n shouldn't be 0? Well, the problem with 0 is that by our definition, 0 is divisible by everything. So everything changes. If you took n to be 0, suddenly everything goes into it. Okay? if, here I assumed n was positive. If n is negative, then the divisors of n are the same as the divisors of minus n. So n and minus n have the same factors. So we may as well reduce to this case where we take a positive integer, and then positive factors of positive integer are going to be between 1 and n. And of course, only some of those will be factors, usually. And that's finally many. But if n is 0, then everything divides into n, because 0 is 0 times anything you like. 0 is divisible by 1,000 because 0 over 1,000 is an integer, namely 0, by our definition. Right. Okay. Now, we now go to another integer m, and we can let m be 0 if we like, because there are only going to be finally many factors common to both of them. Right. So once n's got only finally many possible factors, m can have as many factors as you like, but if you're looking for factors that are factors of both of them, then you can't get more than you had factors of n in the first place. So there's only going to be finally many common positive factors. So that's positive integers which divide both of them. But if m and n are both 0, this goes completely haywire again. If m and n are both 0, then everything, a million divides into 0 and into 0. So the highest common factor of 0 and 0 doesn't make much sense, because everything goes into 0 and everything goes into 0. M and n are allowed to be equal otherwise, though. The highest common factor of 3 and 3 is 3. That's not a problem. But the highest common factor of 0 and 0 doesn't make sense. So all you do for this module, I mean, there's another definition available in the books of highest common factor and greatest common divisor, and we'll see a bit more about that. For the sake of this module, I'm going for this really easy one. You list all the common positive factors. So forget about the negative ones, but they're not going to help anyway. And then you take the maximum one of them. So you list all those numbers that divide into both m and into n. And there's only going to be finally many because I made sure they weren't both 0. One of them can be 0 as long as the other one isn't. Finally many common factors, and you take the maximum one, the greatest common divisor, or the highest common factor, as it's called. I asked for the definition of highest common factor in the exam last year, and very few people could give me a straightforward answer. So if I do ask the definition of highest common factor, I suggest you go for just the definition I've given you here. You're allowed, if I've given you a standard definition and I ask for that definition in the exam, you can give the definition I gave. That's fine. Or anything else that means the same thing. As long as it's clear and unambiguous and correct. Right, so just to make sure that you've got some idea of highest common factor, we have introduced the possibility that the integers you're taking the highest common factor of can be negative. But, so here's your first little question, and I'll give you a couple of minutes to talk, maybe just 1 minute, to talk about this one, and see whether you can come up with an answer based on the definition, right? I've given you a definition of what the highest common factor is, so you should find all the common positive factors of these two, and find the biggest common positive factor, and that will be the highest common factor. Okay? So have a go at that. You've got 1 minute, and I've zeroed the answers, so you should be able to vote any time. I have to wait 10 seconds. Yes, as I was just saying, so the only common positive factors here are 1, 3, and 9. And so you take the maximum of those three, you get 9, and that's the correct answer. Okay, let's have another look at the rational numbers. I sent an email around about the fact that things can be in a set more than once, but that it only counts once. Okay, so when you see this thing, all the numbers you can get by dividing m by n when m is an integer and n is a positive integer, you know you can get lots of things in lots of different ways, like a half is equal to 2/4 equals 4 3/6 and so on. Okay, but it doesn't matter. What Q is it's a set of, you have to decide which real numbers are in Q, basically. And a real number is in Q if it is one of these. So this only counts once. The number a half is in Q, these are all equal, and it's just one element of Q, even though you found lots of different ways of getting it. However, there is a way to make it have a unique expression, which is to write it in what's called lowest terms, which is something you've probably been doing since primary school, I'm not sure. Not sure when you first started writing fractions in lowest terms, but you just try and cancel as much as you can, and you keep cancelling if you find a factor, until eventually you can't find any factors, and then it must be in lowest terms. The fact that lowest terms is unique is not so obvious, and in fact that's probably a consequence of the fundamental theorem of arithmetic that we're going to be looking at later. But we'll take it for the moment for granted that you can put things in lowest terms in at least one way, and in fact it's unique. So you take any rational number x, and you keep counting as much as you can from the top of the bottom, and you write it in this form. So we want to make sure the denominator q is going to be positive. That already stops you from dividing by negative integers, which will still give you rational numbers, but I'm insisting that we put it in do this with a positive denominator. The numerator, the thing on top, can be any integer, but then we have to cancel common factors. So get a different colour. Right, so if you did that sort of minus 27 over minus 36, that wouldn't be in the right form at all. We'd start by writing that as 27 over 36 to get the denominator positive. Then what you do is you take the highest common factor of the top and bottom and divide that out, and you get that down to what's that? That should be there. Okay, so that's equal to 3/4. And that's now in its lowest terms. And minus 6 over minus 4 is a rational number. That's a rational number, but it's not in the right form at all. We write it as minus 6 over 4 to start with, to get the denominator positive, and then you cancel out the common factors and you get minus 3 over 2. And now that's in lowest terms. And it turns out that, so first, if you make the denominator positive, which you can by using the signs, and then you divide top and bottom by the highest common factor of the top and the bottom, then you're fine. And it always works. But I'll leave it to you to think about it a bit more. We'll take it for granted you can do this because you've been doing it since primary school. The fact that it's unique is, as I say, rather more challenging, and you should come back and look at that again when we prove the well, we don't quite prove the fundamental theorem of arithmetic in this module, but we come very close. Right, now, I've given you a warning about backwards logic and how dangerous it is to start by writing down the thing you want to prove at the beginning and making deductions from it, and how that could be a complete disaster. How, if you write something false down, you may deduce something true from it, and that doesn't help at all. And if you write something true down, let's get this right. If you write something true down and deduce something true from it, but you've gone backwards, it doesn't help prove, it doesn't show that the statement you write down at the end implies the statement you had at the beginning, unless your steps are reversible. Okay, but let's take it as reasonable. Not all mathematicians agree with this, but we're going to assume that this one works, that if you start from true statements, you shouldn't be able to deduce a false one. Okay? Well, I think most people agree with that one, but let's have a look at this, what we call indirect proofs, which are proofs by contradiction. So the idea is that if you make lots of deductions and you end up with nonsense, then you must have assumed something wrong somewhere. If you only made one assumption you weren't sure about, and you made deductions and you got nonsense, then the one assumption you weren't sure about must have been false. And that can be useful if that's something you wanted to prove false. So let's have a look at that. You start by writing down a statement and you're not sure whether it's true or false. And now you start making deductions based on that and other standard things that you know to be true. And now you arrive at two other statements which contradict each other, like you discover that x equals 2 and x equals 3, somewhere along the line. Okay? Now, since 2 shouldn't be equal to 3, that suggests that something beforehand wasn't true. But you've only made one assumption. It's important that you only make one assumption beforehand that you're not sure about. And then you know that that assumption must have been false because you've arrived at nonsense. And that's the essence of proof by contradiction or indirect proof. So you mustn't start by writing down the thing you want to prove true and make deductions from it, because that's not going to help you. But you are allowed to write down the statement that you want to prove false and make deductions from that, because that might help you. So let's see how it works in an easy example. This is a particularly easy example which we could actually do rather than by contradiction. You could do this one by using what you could almost call contraposition. You'll see in analytical and computational foundations, you will discover that if you've got a statement then, and it's true, if you know a statement's true, then the contrapositive of that statement will be true as well. So that would be an alternative approach to this. But I want to show you a really easy version of proof by contradiction. So this is one of the easiest one I can think of. We're going to use a standard fact, though, which we proved earlier, which is that the square of every odd number is odd. Okay? So we're going to use this. We're not proving that again. And now I'm going to prove this lemma. Let n be an integer so that n squared is even. I'm going to prove that n must be even. Okay? So we're given that n squared is even. Right? That's our information. Now I'm going to suppose for contradiction, this is, there are lots of ways of phrasing this bit, but it's a good idea to make it very clear where your dodgy assumption is so that you know what it is you've contradicted later. So I'm going to write it this way. Suppose for contradiction, though I know some people who like to say suppose or assume towards a contradiction or various versions of this. But I've always written suppose for contradiction. It'll do for me. That n is not even. Which? And that's the one we want to be false. Okay? So we hope to get nonsense from this. Then n is odd. Okay? Okay, we were told that n is an integer. So an integer that's not even must be odd. And now we know the square of an odd number is always odd. That's a standard fact. Standard fact. The square of an odd number is odd. Well, okay. I'll say n squared must also be odd. But we're told that n squared is even. Okay? So that's a contradiction. What symbol you like to use for a contradiction is up to you. Some people write two arrows pointing at each other for a contradiction. Some people write this symbol. Or you can just say, this is a contradiction. Doesn't matter which of those you do. Okay? Whatever you do, this is a contradiction, which means that your original assumption must have been false. Your original assumption that n is not even is false. So n is even. This is a particularly easy example. So this contradiction shows our original assumption that n is not even is false, thus n is even, which ends the proof. Okay? If n squared is even, then n must be even. That's different from the result we had earlier, that if n is even, then n squared is a multiple of 4. So notice here, something interesting happens. If n squared is even, then n must be even. And earlier, that showed that n squared has to be a multiple of 4. So if n squared is even, then n squared has to be a multiple of 4, which you probably knew anyway. Any questions about that proof by contradiction? Okay, so that's our first one. Now, our task now is to prove that the square root of 2 is irrational. This will be our first example of an irrational number. So, what is an irrational number? It's a real number which is not a rational number. Okay? It's not just a number that's not a rational number, because there are lots of complex numbers that are not rational numbers as well. And they don't count. So the irrational numbers is not just any old kind of number that's not a rational number. It has to be a real number that's not a rational number. Okay? So that's an important fact. So now, the real numbers get chopped up into two kinds of number, the rational numbers and the irrational numbers. In some ways, there are a lot of similarities, because wherever you look, we're going to see, there's rational numbers and irrational numbers all over the place. And they're both what they call dents in the real line. Every interval you look in is full of irrational numbers and rational numbers all over it. Okay? However, it will turn out at the end of the module that there are more irrational numbers than rational numbers, even so. The rational numbers are what's called a countable infinity, and the irrational numbers are an example of what's called an uncountable infinity, so it's bigger. But we won't find that out till the end of the module. Right, so that's somewhere we're going later. But for now, what we need to know is that there's at least one irrational number. That's a good start. If you want to show there's more, that there's lots of irrational numbers, you better have at least one. So we're going to prove that the square root of 2 is irrational. This proof was known to the ancient Greeks, though I don't think they liked it, because I think they really wanted to find everything as a nice fraction, and it was a nuisance to them that they couldn't manage, for example, square root of a half as a decent fraction, and they managed to show it wasn't possible. Okay, so how do we prove that the square root of 2 is irrational? We're going to do it by an indirect proof, by supposing it's rational. Then we're going to use lowest terms to say then it can be written in some form. And then we're going to make some deductions which will lead to some nonsense, as you'll see. And then we'll only make one initial assumption, which will be that the square root of 2 is rational. So that will be the thing that will turn out to be false. So suppose for contradiction, we're going to use all the earlier stuff we've already done, by the way, so I'm going to keep going in on earlier stuff that we've used earlier. Yes. Suppose for contradiction, this is the proof. Suppose for contradiction that the square root of 2 is in Q. That's the same as saying it's rational. Okay? Then there are, well, let's see, using this rational number can be written in lowest terms. Let's say it that way. So this is the supposition for contradiction, but having assumed that, then root 2 can be written in lowest terms. We've assumed it's rational, so then you can write it in its lowest terms. As square root of 2 equals p over q, where p is in, officially p is in z, q is in n, and the highest common factor, HCF, highest common factor, saves a bit of writing, the HCF of p and q is 1. It's rather important that you cancel everything out you can at the beginning. Okay? We're going to do some manipulations and get a contradiction. You can, if you like, note that actually p is in n as well, because this is the non-negative square root. Non-negative square root, it's therefore in fact positive, and therefore since q is positive, p better be positive as well. It doesn't actually matter. Okay? But if you wanted to, you could say that actually p is in the natural numbers. Doesn't matter. Okay, we want to manipulate this. Then, okay, we've got root 2 equals p over q, and the highest common factor is 1. We're going to get a contradiction from that in a bit. Square both sides, which loses information in theory, though not here. We get 2 equals p squared over q squared. But so far that's a statement about rational numbers. But I want to get a statement about integers, because statements about integers are easier to work with. So we get 2q squared equals p squared. Right. Well, 2q squared is p squared. These are integers. I wouldn't make sure you don't ever say that a rational number. Don't start talking about rational numbers which are even or odd. That would be a bad move. But once we've got integers, we can talk about even and odd. And the left-hand side is twice an integer. So the left-hand side is even. So the right-hand side is even. So from this expression, I'll put in brackets. Note both integers. We're only using integers now. The expression involves integers. It's not good to look at, you don't want to look at this first one and say something like p squared over q squared is even, so p over q is even, or something like that would not be a good thing, okay? Make sure everything is integers you're talking about. So p squared is even, and by the result we just proved, if p squared is even, then p must be even. Then p squared is even, because it's equal to 2q squared. So, by our lemma, which you can quote as a standard fact if you need to, p is even. So if you don't want to say by our lemma, you can say it's a standard fact. I mean, unless you're being asked to prove it, you're allowed to quote that if something squared is even, then the number has to be even. Unless the question says, show that if p squared is even, then p must be even. Because you must never assume a result, you must never quote a result to prove itself. Okay, now, so p is equal to 2r for some integer r. That's what even means. Well, maybe we used K before, but it's R now, okay? Doesn't matter. Let's go back and use star again. So substitute into star to obtain 2q squared equals 2r, that's p, all squared, equals 4r squared. And so that makes q squared. Is there a problem or something that you can't read? Sorry. Is there a question anywhere? Okay. Divide through by 2, you get q squared equals 2r squared. So what can we do now? Any suggestions? Yeah? So q squared's even. And hence q is even. By the same standard factors before. But now we've got a problem. P is even and q is even, so 2 is a common factor. So 2 is a common factor. P and q. But we said that the highest common factor of P and Q was 1. This contradicts the choice of P and Q. The HCF of P and Q so that's a contradiction. But we only made one dodgy assumption, which was that square root of 2 was rational. And everything else we've done is a perfectly fair deduction from that, and we've got a contradiction. So the fact that square root of 2, so assuming that square root of 2 is rational leads to a contradiction, so it can't be true. And that's the bit that not everybody accepts. There are mathematicians who don't accept that statements are either true or false. We're going to work with proof by contradiction, otherwise you lose a whole mass of mathematics. So we'll stick to using proof by contradiction throughout pure mathematics. So thus root 2 must be rational. Must be irrational. Okay, any questions about that, our first significant indirect proof in the module?